Hello everyone, I'm Neeraj Kumar from CSC B section. Today my topic is about silicon rubbers. We encounter silicons every day, though we hardly ever notice them. Under the hood, silicon rubber protects the car electronics against moisture and dirt. In car lacquers, silicone additives provide gloss. In washing machines, silicone anti-foam agents prevent the detergent from foaming over. In shampoo, they give hair itchy. They provide woolen garments with a typical soft and a silicone resin emulsion paint. They give Mazzoni water repellency while allowing water vapor and carbon dioxide to diffuse out of its interior. Silicones are perform superbly in medical applications where high resistance or state-of-the-art product is required. It is a highly pure material for medical tubes, plasters, or orthopedic products as a reliable sealant and insulating material in electrical equipment or insulators. Pyrogenic silica is also used as a thickening additive in adhesive for the rotor blades of wind generators. This outstanding versatility is the result of silicon chemistry. Silicones are modern synthetic products based on a raw material, quartz sand, which is available in practically unlimited quantities. Their versatile performance is due to the chemical structure and the many different ways it can be modified. As a result, silicones can be provided with tailor-made properties that are fascinating and other offer continually new possibilities. On the following pages, let us guide you through the world of silicon, discovery the unique chemical and physical properties, and gain insights into the versatile applications they open up. From raw material to the product, chemistry of silicon and its compound is extremely dynamic. Hardly any technology in recent decades has shaped technical progress so strikingly as silicon chemistry. The success story begins with the element silicon. Elementary facts of silicons. In nature, silicon occurs exclusively in oxidized form as the compound silicon dioxide and silica. Silicon is the second commonest element in the Earth's solid crust, accounting for 25.8% by weight and the most important component of inorganic material. Silicon is very rare, found as an element in nature. It was not isolated until relatively recently. On the other hand, Silicious construction and engineering materials. Silicious construction and engineering materials such as sand, clay, and ceramics have been available since the immemorial. Silicon chemistry is very efficient. In 1940 to 1941, Professors Miller and Rocha independently discovered how to react silicon with methyl chloride gas (CS3Cl) to form liquid methyl chlorosilanes. The step provided the standing materials for the industrial manufacturing of silicons and launched a global boom in silicon production. Based on the pioneering work of Dr. Siegfried Nietzsche-Wacker in 1947 became the first European company to start researching the field. In the following years, Wacker processes laid the cornerstone for the modern and efficient manufacturing of organochlorosilanes silicon products. This was the beginning of the success story. These early scientific accomplishments under Wacker's reputation as European pioneer of silicon chemistry, now globally active. The group uses complex chemical processes to manufacture versatile product classes such as silicon fluids, resins, or elastomer compounds. Flowchart shows the production scheme for Wacker silicon. Since the raw materials coal and sand are kept in electrical furnace, then silicon is obtained, and that silicon will go for reactor. This is known as Muller-Rothschild method. Then crude silane mixture is obtained. After that, silane distillation is done. Then we get methyl chlorosilanes. That the whole process The final products are silicon fluids, mold release agents, textile finishes, silicon rubber compounds, RTV1 sealants, highly flexible elementary building blocks. The term silicon was coined by F.S. Kipping (1863 to 1949) and refers to the formal analogy between the silicon compounds and equivalent oxygen compounds of carbon, polysilico-ketones. However, the SiOs group is better described by the term siloxane. Strictly speaking, therefore, all silicones should correctly the term polysiloxane. Nowadays, the term silicone is principally used in conjunction with the technical applications of polysiloxanes. Now let's discuss about the structure of silicon. Silicon, known to chemists as polydiagonosiloxanes, are a structure that resembles quartz modified with organic groups. They consist of an inorganic backbone built up of alternating silicon and oxygen atoms. The other two bonds of the silicon atoms are occupied with organic groups, preferably methyls, which are responsible for silicon's semi-organic materials. Silanes are the starting point. Starting point and chief building blocks for silicon production are silanes. Silanes are produced by direct synthesis from silicon and methyl chloride, Muller-Rocha synthesis. They are colorless, clear, mobile liquids that are soluble in organic solvents, including anhydrous alcohol in certain cases. The low molecular mass of silanes make them highly volatile. Structural variety as a formula. Silicon chemists distinguish between four different structural units. First one shows monofunctional units. Second one shows difunctional units. These are trifunctional units and tetrafunctional units of silicones. The structure of dimethyl dichlorosilane and polydimethyl siloxane from semi-organic plastics. Silicones are a special group of plastics. The term plastic is normally used to refer to organic materials that do not occur in nature. Silicones are classed as semi-organic materials since the element silicon has a strong metallic character compared to carbon. Remarkable stability. The SiO bond energy is significantly greater than that of CC bond. This has far-reaching effects on the stability and resistance of silicones to a variety of influences. For example, silicon have remarkable thermal and thermo-oxidative resistance. Silicones are also far less readily attacked by electromagnetic and particle radiation (UV, alpha, beta, and gamma) than organic plastics. Versatile formula. Silicon's chemical structure allows them to be produced in a number of variations. By using siloxane units with different valences, product can be made with oily, polymeric, resinous, or cross-linked properties. At the same time, the organic groups bound to the silicon pave the way for a diverse range of modifications. It is this variability that makes possible the impressive variety of silicon products, freezes, release agents, anti-foam agents, paint additives, paper coating, hydrophobic agents, high or room temperature vulcanization silicon rubbers, and many, many more. The slide shows applications of silicons. Silicons are applicable at automotive and transport, like FPGA formed and queued in place gaskets, cylinder head, radiators, viscous clutches, headlamps, air filters, vibration dampers, airbag, and etc. And in construction sites like colorless water repellent treatment of facades and concrete, to jointing tapes, textile leather and fibers, plasticizers and elastomers, water repellent treatment, fine coating, fiber fill finishing, fiber preparation, sieving thread lubricant, deforming, paper film coatings and NI, release papers, release liners, films, user oils, roll bells, toners, printing inks, life science, chemicals, food industry, respirator bellows, smoke, prosthetics, dental impression compounds, and etc. Consumer care, hair care, skin care to detergents and cleaning agents. Elastomers, plastics and composites, molded articles, extruded articles, cable manufacturing and sheathing, plastic additives, impregnating agents, polyethylene curing, precision casting. Chemical industry, wastewater, petroleum industry, slags, welding filler materials, tire release agents, energy, electrics and electronics, composite insulators, insulator coatings, cable accessories, transformers, semiconductor industries, consumer and power electronic, photovoltaics, measuring instruments, coatings and adhesives, extremely heat resistant coatings, tabular radiators, corrosion protection, foil coating, glass jugs, electromagnets, and lightning technology. These are the main and major applications of silicones in our day-to-day lives. Chemical structure and properties. Silicon fluids principally consist of chains of alternating silicon and oxygen atoms with the free valencies of silicon compound occupied with organic radicals are usually methyl groups, though in special cases they may also be phenyl, vinyl or amino groups. Silicon fluids are transparent, tasteless and odorless liquids which no known harmful effects. Their viscosity lies between 0.65 to and 10 lakh millimeter square per second, depending upon the type. They have excellent thermal resistance from -62 to +300 degrees Celsius. Silicon fluids are also characterized by very low volatility, excellent shearing resistance, low surface tension, and very good water repellency. Another important feature, of course, is their remarkable electrical properties over wide temperature range. The most widespread orthofunctional silanes are alkoxy silanes with a propellant spacer between the silicon atom and the functional group X. The most important functional groups are aminoglycidoxysulfur, methacryloxy, and vinyl. In recent years, alpha silanes have gained increasing importance instead of the customary propellant spacers. These alpha silanes have a methylene bridge between the silicon atom and the functional group, making them much more reactive than conventional gamma signals. The increased reactivity of the epoxy has several advantages. Not only does it open up new applications for alpha silanes, such as fast setting adhesives, but it also makes them interesting building blocks for use in established applications. Silicon fluids are ideal for us as hydraulic transformer oils, damping liquids, diffusion pump of fluids, thermally resistant lubricants, electrics, deformers and release agents for photocopiers and laser printers. They can also be used for hydrophobic treatment of glass and mineral wool. Especially silicon fluids can be processed into impregnating agents for textiles and leathers. They are also used in very small amounts as paint additives. Other important applications are to be found in cosmetics, pharmaceuticals, and medicine. Organofunctional silanes are the main ingredients of almost all adhesives and sealants. As adhesion promoters and curing agents, they improve the physical and mechanical properties and increase chemical resistance. In the plastic industry, vinyl silanes are used for silane curing and producing cross-linkable polyolefin compounds. With their high reactivity, alpha silane curing agents can now be used for ecological, user-friendly formulations without tin catalysts and solvents. Organofunctional silanes have become indispensable, particularly in coatings, paints, and lacquers. Here, they are used as adhesion promoter or curing agent. But the most important application of organofunctional silanes is as surface modifiers or inorganic materials, such as mineral fillers and glass fibers. Silicon antifoam agents, chemical structure and properties. Silicon antifoam agents too are based on silicon fluids. The antifoam activity is created by adding various substances in the form of activators. Usually fumed silicas, because of their extremely low surface tension, silicon and deform agents can spread on foam lamellae and displace the surfactant molecule that stabilize the foam. This causes local weakening of the foam lamellae. The solid hydrophobic components of antifoam agents are transported along with silicon droplets into the foam lamellae, further destabilizing the lamellae. The effects rupture the foam lamellae and cause breakdown of the foam. In contrast to organodeformers, silicon antifoam agents are highly efficient, chemically resistant, and thermally stable. Antifoam agents can be used for effective foam control in a wide variety of industries, from the chemical, photochemical, petrochemical, dye, and coatings industries through detergent production, textiles, and cellulose to water waste treatment. That's all about silicone rubbers. Hope you enjoyed and gained some knowledge regarding silicone rubbers, their manufacturing processes, and applications of silicone rubber. Thank you.